All right, so up to this point, we've looked at linearization, we've looked at Newton's method, and then today we're going to talk about differentials. All three of these are infinitely linked together because they're all ultimately relating back to the tangent line. So the tangent line itself has helped us look at problems and look at their derivatives and be able to approximate what is occurring on the problem. So a differential is simply another way of saying an approximation that we can't calculate by hand any other way. So if we use a tangent line to approximate a curve, it gives us a relatively good estimate as long as we don't go too far away from the center point. So differentials and linearization really go hand in hand. So we kind of started with linearization, hit Newton's, and we're going back to differentials because we're changing the notation. We're changing the way we look at the problem. So considering the function f, and we have this point on its center, we're going to talk about how the tangent line and the differentials relate in respect to talking about delta y and delta x. So here's our function f, and on function f we have some point c. So I already marked C for you so that everybody's C would be at the same spot. So function f, point C. So if this is point C on function f, then that means over here on the y-axis, this is the same as saying f of c. Because if the function itself is y equals f of x, if you plug c in, you get f of c. So consider the function f and label the center point C f of c and draw the tangent line to the point. So is this graph concave up or concave down? Concave up. If you have a concave up increasing function, is your tangent line going to lie above or below it? Below, which means my tangent line is an over or an underestimate. Under. So my tangent line that I draw in will be below my curve, and it's going to be an underestimate of the curve. So thinking about my tangent line and thinking about the graph f, how could I write an equation for my tangent line? What do we know about the tangent line and its equation? Well, isn't an equation of a tangent line simply y minus y1? So in this case, isn't y1 f of c? So it's y minus f of c equals, isn't the slope at this point on the tangent line the derivative of the function at that point? So it's f prime of c represents my slope. And then we talk about the change in x with respect to c. So the slope in the equation for my tangent line becomes y minus f of c equals f prime of c x minus c. Does that not look like linearization, but instead of a's, we have c's? What we're doing again is now we want to talk about moving delta x to the right of c. So differentials are saying, how far away can I get from this point and my line still give me a good approximation? So when we talk about like linear approximation and differentials, we talk about the change in the value of x, and we try to use that to approximate the slope right here. So now we're saying, okay, if I make delta x to the right of c, so let's make some new point, and we'll call this new point over here delta x. We've moved delta x units to the right of c. So this point in terms of my function would be delta x plus c, because the distance here is delta x. So we want to move delta x to the right of c, which makes my new point delta x plus c. What's that make the y value at this new point? Not on my original function now, though, but on my tangent line. So now I'm going up to this, and I'm going to the tangent line. And I want to find the value at the tangent line, not on x. Exactly. So like what I'm doing is I'm saying, how far away from C can I get that my tangent line will still be a good approximation of F without having to recalculate a new tangent line, basically. So how far can you go away from C to predict the slope of F? That's kind of what we're looking at right now, is we're saying.
I just don't understand what's the point of that.
So we have C, and we have the slope at C.
Yeah.
I want to know the slope of F at delta x units to the right of C. So I'm still trying to predict the slope of F here, but let's say I don't know what the function F is here.
You don't know the point.
Like I don't know the point or the value.
You're trying to predict it based off of C.
Exactly. So I'm trying to use the tangent line and the points I do know to predict the slope of F at this point here. That's kind of like what we're getting at, is how far away can I be and still be accurate? So what we would do is we would plug this in to F on my tangent line. So this would become y minus F of delta x plus C equals F prime of delta x plus C times the quantity of C minus delta x plus C. So what I've done is I've replaced all the C's with the delta x plus C, and my x became C. So that this value right here, what happens to C and, oh, it should be in parentheses. So that it's x minus all of this. So your C's will cancel. So you end up with y minus f of delta x plus c equals negative f prime of delta x plus c times delta x. So that makes my actual change in this given by f of, which is exactly what you predicted, f of c plus delta x. Because once you start to look at these and you talk about the changes and you plug in actual values, they will ultimately give f of c plus delta x. So once you plug these in, no, but if you plug in the actual values for these, this will zero out and you'll get y equals f of delta x plus c. You'll see, we're going to do an example with actual numbers. This is like here's the general, here's the actual. So
They will though, because
they will. If they don't, yes. So when delta x is very, very small, and we're talking like infinitesimally small, we can say, infinitesimally? Yeah. We can say that delta x equals dx. So what we're doing is we're going into the notation of lightness. So go back and think about when we talk about derivatives. And I said, okay, move away from f prime and y prime and move into dy dx. So a differential is that dx part. So when we talk about derivatives, we're talking about differentials. So we're talking about the derivative of y with respect to x. But you never really knew what that respect to x meant. Well, that respect to x is what we call a differential. It is an infinitesimally small change in x. So we call that dx, dy dx, we call that dx the change in x that's infinitesimally small. We denote the approximation as change in y with dy. So find dy. So let's go back and let's talk about f prime of x. Didn't I just tell you that we changed our notation of f prime of x to dy dx? And that dy dx, we've always said, is a derivative is what? By definition, a derivative is what? slope of the tangent line. What's a description for slope? Go back to the elementary definition of it. Rise over run, or like even, okay, like change in y. So like when you read word problems, how did you know what represented the slope versus what was the y-intercept? What were some key words that helped you get to the slope? I'm trying to even think like, okay, but like even like more as like descriptors. So like even when you, okay, think about velocity in physics. What are the units on velocity? Meters per second or miles per hour. What do we call those units? We also refer to them as, I know we've done it a billion times. What was our last unit in here? What was 4.6? What was that section called? Rates. So like rates of change is derivatives. Those were rates, miles per hour, meters per second. Those are rates, they're rates of change. Derivatives represents rates of change. So when we talk about this, this is a rate of change. So dy dx is equal to f prime of x. Y is equal to f of x. So what's dy going to equal? Well, dy is f prime of x times dx. It's the slope times the change in x. So dy, if we solved this, we cross multiply, get the dx over there. Dy, and again, we talked about this with linearization. Dy, which is the change in y with respect to x, is the derivative of the function times that tiny little change in x. So Leibniz used dy dx to represent the derivative of y with respect to x. Differentials allow us to treat that dy and dx terms of the notation as separate terms. Finding a differential is simply finding a derivative using a different notation. So we're going back. You kind of start chapter 4 with derivatives, we end chapter 4 with derivatives. We're just deriving in a slightly different way. Everything we do is derivatives. So we're told now that dx, that dx part of a derivative, is equal to 0.01. We've never been told something like that before. So now, like if you wrote dy dx, you'd kind of be writing dy over 0.1. We're saying that differential, that tiny space in time, is 0.01. And x equals 2. If y equals f or x to the 5th minus 4x cubed. So remember, dy dx, that represents a derivative, right? So dy dx has to equal the derivative. So what's the derivative? Well, it's 5x to the 4th minus 12x squared. So if I want to know what the differential dy is, I'm just going to multiply both sides by that 0.01. So differential dy is 5x to the 4th minus 12x squared times 0.01. This 0.01 is me looking at my function, finding its tangent line at x equals 2, and then moving 0.01 units beyond it. So here's the 0.01 units away. I found this at x equals 2. And then I moved 0.01 units away and found the new derivative. So 16 times 5 minus 2 squared is 4. 4 times 12 is 48. So 80 minus 48 is 32. And again, 0.01, kind of like 1 over 100. Or you can think about if you multiply 32 times 1, you get 32. 32 times 0.1 would be 3.2. So 32 times 0.01 adds 2 decimals and turns this into 0.32. Like I said, like it's actually like we kind of started really easy and we end really easy. What I want you to take away is the interpretation. Can you put this into words? So in terms of words, what does this mean? It means that if x equals 2, so if x equals 2, and then it changes to 2.01, because we moved 0.01 units to the right, or we could have moved 0.01 units to the left, but in this case, I added it and moved to the right because I kept it positive. So it means if we go to 2.01, then the y value increases by 0.32. So this 0.32 represents the increase in y. Go back to what you told me about slope. It was change in y over change in x. So the y value changes because this is dy. This is dy. That's what we solved for. It means the y value changes by 0.32 when the x value changes by 0.01. dy dx. It's our slope. It's our rise over run. So it rises up 0.32 when we run 0.01. Again, it's not precise because we are approximating, but that's what the derivative is saying. The derivative is saying we are changing by 0.32 on y as we change by 0.01 on x. Let's talk about it in terms of trig. Let's talk about how trig functions change along the unit circle. Because again, it's a circle. Everything is curved. It's not flat line, so we can't really talk about rise over run because you're rising and running in a circular pattern. So what happens if we want to find the differential dy for y equals the sine of 3x when x equals pi? So think about the unit circle. Think about where pi is. Pi is way over here, right? So in terms of the unit circle, if we're running around our unit circle, pi is over here. If you turn this into a sine function, pi ends up being right smack in the middle. So think about what we know about this function in terms of derivatives. This pi point becomes a point of what? Inflection. It's changing from concave down to concave up. We have a point of inflection. What's the 3 do to the sine function? What's that 3 do in terms of our sine function? So we're going to talk about your phase shifting and stuff again. So exactly, it's going to change your period. So you said it makes it more frequent, and it does. It shrinks the period, right? Because the idea is that you would set 3x equal to 2 pi, and now my pi is 2 pi thirds instead of my period being 2 pi. So it shrinks that period by like a third-ish type manner. So that means this cycle is happening faster and faster than it would normally. So it just kind of makes it oscillates more. Okay. Okay, so what's dy dx? Well, we have to find dy dx and then kind of go back and solve for dy dx. So what's the derivative of sine of 3x? What's the derivative of sine? So remember that this is a chain rule, so you get cosine of 3x times 3, because you got to multiply by the derivative of the inside. So dy dx in general is 3 cosine 3x. So what that means is the change in y over the change in x is 3 cosine 3x. Now I want to more specifically know what's the change in y when the change in x is negative 0.02. So I'm going backwards, right? So I want to know what's the change in y when my x value is pi, but not pi, because I want to know what pi minus 0.02. So like I'm going backwards 0.02 units from pi. So I'm going to a trig value I don't know, but what I'm doing is I'm using a differential to make the trig value something I do know. So I'm not actually finding the tangent line right here at pi, because what do we know about the tangent line at pi? What's the tangent line at this point on the unit circle? What's the tangent line right here? It's undefined, because the slope of the tangent is undefined, therefore the tangent line is undefined. So I'm not finding the undefined tangent, because I already know that, because it's point of inflection. I'm finding it, yeah, like 0.2 units before the pi. So like I'm not finding it at pi, I'm finding it right here at pi minus 0.02. Because it's negative, I went to the left. So what do you know about the cosine of 3 pi? Think about your unit circle. That's going to put you right back here at pi, so it's negative 1. So you get 3, negative 1, negative 0.02. So 3 times negative 1 is negative 3. Negative 3 times negative 0.02. Yep, exactly, 0.06. Let's say just think about 3 times 2, adding back your decimals. So that means that as we go negative 0.02 units to the left, y is changing by 0.06 units, increasing. So this means y, because it's positive, is increasing. So y is increasing as x decreases. This unit brings it all together, right? We've hit trig right now. We hit differentials. We hit derivatives. We talked about what the derivative represents truly at the heart of all things. What's one other? We talked about related rates. Another concept that we hit in chapter 4 was deriving using implicit differentiation, meaning that the x's and y's were stuck together. I couldn't solve explicitly for y. I had to use this rule where I said, all right, I can take the product rule and I can derive everything with respect to x, but that's going to give me dx dx's and dy dx's. So now I want to find, I'm still looking for and hunting down dy. Because I know that dx is increasing by 0.05. So that means I'm moving 0.05 units to the right of my original x, which is pi. So again, I got some trig going on. What is dy when dx is 0.05? Well, I got to derive this. So I'm going to derive it with respect to dx. So what's the derivative of x? Yeah, so derivative of x is 1 dx dx. Don't lose that 1. Don't lose it, because if you do, you'll hurt your problem. The derivative of y is dy dx. Yeah, it's 1. I just didn't want you, because the dx dx's cancel out, I didn't want you to not see the 1. And we're not going to cancel away our dy dx. Over here is a product rule. Exactly. Again, we should be pretty good at those because we did them with related rates. we had product rules, and we had all of these, except for when we did related rates, everything was derived with respect to time, because we were talking about change in time. So our differential with related rates was dt, and you were told dt a lot, but you didn't see it as a differential. You saw it as a related rate. So really, we've been doing differentials, we just didn't see them as a differential. Get dy dx alone, because I got to isolate dy. So I'm going to subtract over this dx, this x dy dx, and I'm going to move over my 1. So I end up with 1 dy dx minus x dy dx equals y minus 1, because I 1'd out my dx dx's. GCF dy dx divide by that other stuff. It is implicit, but now instead of finding the rate of change of the entire problem, so the slope or the rate of change of the entire problem would be y minus 1 over 1 minus pi. And then I'd have to go back and say, uh-oh, what was y? Well, I could find y up here by saying pi plus y equals pi y. And again, like solve for y up here. So I'd have to say pi equals pi y minus y. And then say pi equals pi minus 1 by GCFing the y again. And then I get y equals pi divided by pi minus 1. And I have to do this because I need to know what y is over here. So I get pi over pi minus 1 all over 1 minus pi. Just super gross. This right here represents the slope of the tangent line. This represents the total change in y over the total change in x. So I could clean this up algebraically. So I'd have pi minus pi plus 1. So I got a common denominator here. So I multiplied this by pi minus 1 and distributed my negative. So then this becomes pi minus 1 times 1 minus pi. Pi's cancel, and I get 1 over. I pull in a negative. Yeah, minus 1. So I pulled out a negative so I could square the bottom. So exactly, like this is dy dx. This is the slope of the tangent. What I want to know is what's dx or dy when dx is 0.5. So all it is, take this right here, this negative 1 over pi minus 1 squared, and multiply it by 0.05. So you get negative 0.05 all over pi minus 1 squared. Or you could turn it into 5 and put 100 in the denominator. So why, like what's the whole point? Like what does this tell me again? Like why am I looking at these? Because differentials rather, predict change that we cannot find normally. You could not look at your unit circle and predict this 0.06 change. You wouldn't know it, but you can use a differential to find it. So a differential is simply a way of estimating change. And there are times where estimating change can be very important. We're using a differential to estimate change we couldn't otherwise calculate nicely. So we're estimating the changes that we know for a function f of x at a point A, and we want to predict how much it would change if we move dx units to the right or left of A. So we have f of x is differentiable at x equals A, and the approximate change in the value of f when x changes from A to A plus dx is df equals f prime A. Lots of words. So I told you, this is like the culminating unit, right? We looked at implicit, we looked at trig, we looked at a basic derivative. Let's look at related rates. I told you we've already kind of hit on this in related rates without using the related rates as differentials. Let's make that culminating connection. Let's turn related rates into a differential. So let's not talk about maybe time. Let's talk about an increase in its area. So we're not changing it with respect to time, we're changing it with respect to its area. So it says the radius of a circle R increases from 10 meters to 10.1 meters. So that means that your inside circle that I gave you so your interior radius is 10, your exterior radius is 10.1. So it says the radius of a circle increases from 10 to 10.1, using dA to estimate the increase in the circle's area. So I know the change in radius, I want to know the change in area. So compare the estimate with the true. We can find the true change. This isn't something that we can't calculate. We could find it, right? I could look at the area of a circle at 10 and look at the area of a circle at 10.1. But what we want to do is we want to look at an example where we talk about a differential and the comparison of the two. So let's talk about area of a circle. Area of a circle's formula is pi r squared. What's our change in radius? How much is the radius changing? What? Yeah, so no dt because we're going to derive with respect to r this time. So like we're going to talk about dA, dr, because we're not talking about time. I don't have a rate. I have a change in a radius only. So it'd be 2 pi r, because it'd be dr, which would be 1. So it asks me to find dA. So dA would be 2 pi r dr. Now what I was getting at is what is dr? All my other problems have told me dr. They told me what's the differential change. It would be 0.1 because you go from 10 to 10.1. So this is your x. This is your x plus dr, or delta x. So dr would be 0.1. So dA would be 2 pi 0.1. What's my r? Am I plugging in 10? When you plugged in the other values, did I plug in the original or did I plug in what I was trying to find? Plugged in the original. So this is 10 because the 0.1 is allotting for the change. So what's 0.1 times 10? It'd be 1/10 times 10, so it'd be 1. So dA is 2 pi. And if you want to get really specific, we're talking about meters squared because we're talking about area.
Wait a second.
What?
Would you plug in 10 per hour and 0.1 for DR?
I did. I just, when I wrote them, I said it separately. Let's talk about the true change in area. So area of the outside circle compared to area of the inside circle. So the area of the outside would be pi r squared, where r is 10.1. So it'd be pi 10.1 squared minus pi times 10 squared. Anybody know what 10.1 squared is off the top of their head? Without a calculator? I don't know. You'd have to. See, that's where like differentials come into play. We could do all of this math without a calculator, right? Now I'm getting into gross decimals. So you would have to, if you didn't have a calculator, go back to the days of 10.1 times 10.1. Saying, okay, I got to do 1 times 1, 1 times 0, 1 times 1, add a 0, 0, 0, 0, because everything times 0 is 0. Add 2 zeros, get 1, 0, 1 again. So then I got to add these linearly. So you get 1, 0, 2, 0, 1. And I have 2 decimals, so I got to add 2 decimals in. So I get 102.01. So I have 102.01 pi minus 100 pi. So 102.01 minus 100. So 2.01 pi. What did I get? So how, like, I'm relatively close, right? We're talking a 100th off.
So that's what you're asking. Or is that not?
This is actually an underestimate
Oh, yeah,
because my predicted, so my predicted is 2 pi. My actual is 2.01 pi. So I had an underestimate. So what does that tell you probably about the area of the circle? It's considered to be concave. Yeah. All right, looks like I shortened your homework on here. I did one thing. I think 19 to 33 is less than 19 to 25. So let's do 19 to 33. Odd. It's not bad. I did it all in front of the handout.